I want to get a majority of this done. Some of this will also help in that take-home lab that's this week's lab. All right, so we want to start off with another problem here. What is the pH of 0.3 molar formic acid? Okay, so do you guys know how to do this? All right, so this is something that should be a review for you guys. Okay. So first thing, when you're given a problem like this, what you want to do is identify it as a weak acid. Okay, why is it a weak acid? Okay, because it's not one of our 6 strong acids. Alright, so on the quiz and on the exam, first off you're going to write out the chemical formula, the reaction of HCOOH, formic acid, with water. Alright, I'll give you the Ka. The Ka will be given to you, and that's 1.8 times 10 to the minus 4. Alright, and now you'll set up your ice table. Alright, so we did these types of problems in chapter 15. So this is 0.3 molar. Okay, we don't care about the liquid. This is 0, this is 0, this is minus x plus x plus x. So this would be 0.30 minus x plus x and plus x. Alright, so you'll plug that into the Ka. So this is what you'll do for your test, quiz, homework, so on and so forth. Alright, Ka will be given, it's 1.8 times 10 to the minus 4. Alright, HCOOH is x, H3O plus is x times x is x squared, divided by 0.30 minus x. Alright, so what you'll do next here in this class and on the exam is you can use the low ionization assumption. Okay, and that low ionization assumption is that we'll assume x is small. So that 0.30 minus x, okay, is going to be about 0.30. Right, so this makes it 1.8 times 10 to the minus 4 is equal to x squared divided by 0.30. And then let's go ahead and solve for x here by taking the square root. Okay, that equals x. So when I take the square root, I get the answer of 0.00735. So this is x, but what really is x? Okay, this is x, but what does this x symbolize? It's the concentration of HCOO minus, but it's also the concentration of H3O plus. So pH is equal to minus the log of H plus or H3O plus, one and the same. And so this is x, but we found x to be 0.00735, and when I do minus the log of 0.00735, I'm getting a pH of about 2.13. Okay, so this is actually a review of the last chapter. Okay, so this is a review from the last chapter, and it will be on the exam. The new material here is part B. What is the pH when you have 0.3 molar solution of formic acid and 0.52 molar solution of potassium formate? You guys see here? Potassium formate, HCOO minus, and neutralized by the K+. So what we have here is the acid. All right, I'll highlight it in pink. And we have its conjugate base, which is HCOO minus. Okay, this K plus is called a spectator ion. Okay, it's a spectator ion. So we have some of this at 0.3 molar, which is the acid. We have some of this, which is 0.52 molar, the conjugate base. So we'll utilize what's called the Henderson-Hasselbalch equation. All right, so I'll give you that equation on the exam. What is it called when you have a little bit of the weak acid along with its conjugate? We call that a buffer. Okay, nothing strong, no strong acid, no strong base, just a weak acid and its conjugate. So for a buffer, we use a specific formula. We don't have to use an ice table. So here I was using an ice table for part B, but we don't have to do that. We can use the Henderson-Hasselbalch equation instead. So the Henderson-Hasselbalch equation is when you have in the problem HA and A minus present. And the equation is pH is equal to pKa plus the log. Okay, you drop the acid. And the conjugate base goes up on top. I'll give you this equation on the exam. So in this specific problem, part B, we have pH is pKa plus the log of HCOOH and HCOO minus. Okay. So pH is minus the log of Ka. So the Ka for formic acid, I'll give that to you on the test, and I believe it's 1.8 times 10 to the minus 4, but I'll give you the Ka. So minus the log of Ka, the Ka is 1.8 times 10 to the minus 4. Okay, plus log concentration of HCOOH. Now in this problem, the concentration of HCOOH was 0.30. What's the concentration of the conjugate? 0.52. So you'll plug it into this equation. And that will give you the pH of this weak acid conjugate base buffer. So 0.52, 0.30. And that will give you the answer. Okay. So minus the log of 1.84, 1.8 times 10 to the minus 4 is 3.74. Okay, what's the log of 0.2? 0.52 divided by 0.30, 0.238, 0.24. So 3.74 plus 0.24 is going to be about 3.98. All right, so when do we use this equation? We use this equation anytime we have this in the problem, the base, conjugate base, and we have the weak acid and its conjugate. If you have those two concentrations, you'll utilize this equation. Also, the combination of these two is called a buffer. All right, let's do one more problem like this. Calculate the pH of 0.20 molar acetic acid.
So wait, so we use the Henderson-Hasselbalch equation for weak acids and strong bases?
There's nothing strong in a buffer. Okay, weak acid and its conjugate. All right, calculate the pH of 0.2 molar acetic acid, just the same as before. So I'll give you the Ka. Okay, I'll give you that for acetic acid. It's 1.75 times 10 to the minus 5. I'll give you that. pH of 0.2 molar acetic acid. So imagine you have a bottle of acetic acid. Okay, that bottle of acetic acid just does not contain acetic acid by itself. Okay, what else is in that bottle? What else is in that bottle? It reacts, some of that acetic acid will react in that bottle, so that in this bottle you'll not only have acetic acid, but you'll have proton and acetate, right? So this contributes to a pH 0.2 molar. Okay, the liquid is ignored. 0, 0, minus x, plus x, plus x. This is 0.20 minus x. This is plus x and then plus x. All right, this is going to be exactly the same as our previous problem. Ka is going to equal to hydrogen ion acetate divided by acetic acid. All right, plugging things in, 1.75 times 10 to the minus 5. Okay, this H plus is x, this acetate is x, x times x is x squared, this acetic acid is 0.20 minus x. Okay, what will you do now? Okay, we'll do our assumption. This is called the low ionization assumption. So assume x is small, that means 0.2 minus x is about 0.2. So 1.75 times 10 to the minus 5 times 0.2. Okay, we square root that to give you x. And then when I do that on my calculator, I get x equal to 0.00187 molar. Well, what is that 0.00187 molar? That's x. And what does this x really symbolize? What is the concentration of this x? It's the concentration of H3O+. We know our formula for pH is minus the log of H3O+. We'll plug that in and get the answer. All right, so this is what I want you to do on the exam or the quiz. Just to save us some time, I have the answer here as 2.73. Okay, when I plugged it into the calculator. Okay, how about part B? pH of acetic acid at 0.2 molar with 0.3 molar acetate. Okay, so what do we have present? We have present the acid. What else do we have present? Okay, the conjugate of the acid. So what is the conjugate of acetic acid? It's CH3COO minus, which is acetate ion. So what equation can we use for this? Okay, we can use the Henderson-Hasselbalch equation, right? So this equation I'll give you on the exam. Its pH is equal to pKa plus the log of, drop the acid, and the base goes in the numerator, the conjugate base. Okay, so this is minus the log of Ka, which for acetic acid, if you look it up, it's 1.75 times 10 to the minus 5. It's a weak acid. Plus log acetic acid. What is the acetic acid concentration in this problem? Okay, the acetic acid concentration in this problem is 0.2. The acetate ion concentration is 0.30. So log of 0.20, 0.30. Okay. I'll just go ahead and give you that answer on the here, minus log of 1.75 times 10 to the minus 5. I did it on my calculator beforehand, and I got 4.76. Log, if you take 0.30, 0.20, that's 1.5. Log of 1.5, which is this fraction, on my calculator I'm getting 0.176. So when I add them up together, I'm getting about 4.94. Okay, so make sure that your answer, your calculator answer, corresponds to mine. So weak acid and its conjugate gives you a buffer, and then you notice you add the conjugate base here, and the pH goes up. By the way, this is what we call the common ion. Okay, acetate is the common ion. The previous problem here, formate is the common ion. Okay, so the common ion is going to suppress ionization. Okay, that's a major theme here. Common ion will suppress ionization. Move to the side away from ions. All right, so we talked briefly about buffers. Let me just complete this section here. Okay, buffers, I want you guys to know, keep the pH steady. All right, and as Bailey said, well, is a buffer a weak acid and strong base? Okay, it's not that. It's a weak acid and its conjugate. Okay, weak base and its conjugate, weak acid. So if you have those two present in your bottle, it will keep the pH kind of level. You know, you don't want your pH to be too high. You don't want your pH to be too low. A good buffer will do that. And the best buffering capacity is when pKa is equal to, the best buffering capacity is when your pH is equal to pKa plus minus 1.
So all we really need to know is about buffers is that formula right there, and that it just keeps
when your pH is the pKa plus minus 1, that's when it serves best as a buffer. So for example, acetic acid and acetate. Okay, this is a buffer. Acetic acid is this formula. Acetate is this formula. Where does this best serve as a buffer? Okay, the Ka for acetic acid is 1.75 times 10 to the minus 5. If you do minus the log of that, you'll get 4.75. So acetic acid and acetate is the best buffer between 5.75 and 3.75. That's the best buffering capacity. You take the pKa of that acid plus 1 pH unit minus 1 pH unit. This is when acetic acid and acetate is the best buffer. It can withstand pHs between 3.75 and 5.75. You can add a whole bunch of acid. You'll keep the pH between 3.75 and 5.75. You can add a whole bunch of base. It will keep the pH between 3.75 and 5.75. Okay? So this is what we call the best buffering capacity. Right, that's one thing. Another thing I want you to know is that the formula. I'll give you the formula. Okay? I'll give you the formula, but you need to know that you apply it for buffers. Okay? All right. We'll talk more about this when it comes time to do our test review and practice exam. Right now, let's talk about acid-base titrations. This is your problem set. It's a big problem set. I don't know if I told you this, but on your problem set, you can skip KF. Okay, you can skip complex ion formation. So really, what types of Ks did we study? Very good. KB, KA. KC stands for concentration. KP stands for pressure. KW is water, 1 times 10 to the minus 14. And then there's another K called KSP. Okay, there's a KF, which you can skip on your lab problem set. All right, let's begin now with titrations, because I don't know if you've started that problem set or not, but a titration is this. Okay, what you put in the burette is called a titrant. This is what gets dropped, drip by drip by drip. And what goes in the flask is the titrand. So we'll have a strong acid or strong base that we drop using the burette, that long glass tube. And then we'll have a weak acid or a weak base that stays in the flask. Okay? So there's 4 parts to a titration. There's 4 parts. Okay? Okay, the 4 parts of a titration are when nothing is added, okay? That's part 2 of the titration is before the equivalence point. Okay. Part 3 of the titration problem is at the equivalence point. And then part 4 of the problem is when you're after the equivalence point. What is the equivalence point? Okay, the definition of the equivalence point is when your titrant is equal to your titrand. So your concentration of your titrant equals to the concentration of the titrand. All right, so these are the 4 parts of the titration. Let's go ahead and do some of these titration problems now, kind of like what you're doing for the lab. So for that lab, you can work together, work with your partners, and turn in that sheet. All right, so we have exactly 100 mils of HNO2. This is called nitrous acid. Okay, is titrated with 0.10 molar sodium hydroxide, which is a strong base. So if I were to draw this out, you have your burette with NaOH, that's your strong base. And then here you have your HNO2. Okay, so we are dropping NaOH, which is OH minus strong base, into the weak acid. All right, so the first part of the titration is where nothing is added. All you have in part A is 100 mils of 0.10 molar HNO2. So the first part of the titration, you're not adding any of the titrant. Alright, so how will we do this problem? It's just the same as what we've done so many times already. But this HNO2 that's sitting here is the titrand. Okay, we'll react with water. So no OH is added, nothing is added. We'll do our ice table, 0.10 0, 0 minus x plus x plus x, 0.10 minus x, x, and x. Alright, so the Ka is going to be 1.4, I'm sorry, the Ka is 4.5 times 10 to the minus 4. Okay, this is going to equal to x squared divided by 0.10 minus x. Okay, we assume x is small. This is called the low ionization assumption, LIA. So that means because of the low ionization assumption, we assume 0.10 minus x is about 0.10. So 4.5 times 10 to the minus 4 equals x squared divided by 0.10. And I'll just complete this off here. Equals x. Okay, I'm getting x to equal 0.00671 molar. Okay, what is that x? Okay, we should now know that that x is nothing more than the concentration of H3O+. So the pH here is, this problem is minus the log of 0.0067. And what is that on our calculator? 2.17. Okay. Alright, so that's part A, okay, where nothing is added. Alright, what is part B now? Okay, we're starting our titration. And this is before the equivalence point. Now we add 80 milliliters of NaOH. So what did we say NaOH was? Was it a weak base or a strong base? It's a strong base. So the first thing is we have to write our reaction. The minute you add NaOH, this is what happens. This is the reaction. Okay, what will that strong base do, Bailey? Okay, it's going to grab all of this proton. The weak acid donates that proton. And you're going to get H2O liquid plus NO2 minus. So this is the equation for that. We have transferred that H plus. Alright, so what is the concentration of OH minus here? Let's go to part B here. Okay, what's the concentration of OH minus? Alright, so I want everyone to look carefully and be with me here now. Okay, what's the concentration of OH minus? 80 milliliters of 0.1 molar. Okay, so for part B, 80 milliliters. Sorry. Okay, for part B, 80 milliliters of 0.10 molar. Okay, what's our total volume? Okay, we added 80 mils to how much HNO2? 100. So what's our total volume? 180 mils. So this is the concentration after mixing. This is the concentration of the OH after you added 80 milliliters to the 100 milliliters HNO2. So also I want you guys to realize the mils and mils cancel. So what are we left with? 80 mils times 0.1 divided by 180. Alright, the concentration here is 0.04444. Okay. Everyone with me on this so far? 0.0444. Okay, molar. Okay, what's the concentration of HNO2? Okay, everyone look at me now, or look at the piece of paper. We have 100 mils of 0.1 molar HNO2. 100 mils of 0.10 molar HNO2. What is our total volume after mixing? What's our total volume? 100 mils here, 80 mils added in part B, so what's our total volume? 180 milliliters. Okay, I want you guys to recognize that the mils cancel. So what's 100 times 0.1 divided by 180? 0.0556. Okay, that's its concentration. 0.0556 molar. All right. So the concentration here is 0.0556 molar. All right, now comes another question. I need everyone's attention and focus on me here. Can I ask you this question here? I figured out the concentration for a total volume of 180. Okay. And this is the concentrations, okay, after you added the NaOH. Now, my question to you is, I'll ask you, Bailey, since you are receptive. NaOH or OH minus, is it a strong base or a weak base?
It's a strong base.
Yes. So how much of this weak acid will it eat up? Will it take? How much? It's strong. How much will it take up? How much protons will it take away?
It'll take up one. No.
How much? A lot or a little?
A lot.
Okay, how much is a lot? A lot is all of it.
Yeah.
Okay, it's going to take all of it. Why will it take all of it?
Because it's a
Strong base. So how much is all of it? How much? That's all of it. It's going to take 0.0444 molar. Okay? It's going to eat up all the acid. But there's only 0.0444 of the base, so it's going to eat up 0.0444 of the acid. Do you guys see what I'm talking about here? So this is what I mean when I say all of it. It's strong, so it's going to take up all of it. Okay, we don't care about the liquid. And this is going to be plus 0.0444. Excuse me. Okay. So the strong base is going to eat up all the strong acid, But how much of it? All of it. How much is all of it? 0.0444. It can't eat up 0.0556. Why can't it eat 0.0556? Because you only have 0.0444. Okay. So what's 0.0556 minus 0.0444? About 0.0112. And then this is 0.0444. All right, my next question to you guys is, how will we get the pH? We have HNO2 at 0.0112. We have NO2 minus at 0.0444. Okay, what equation can we use if we have the weak acid along with its conjugate? Okay, what equation can we use? I'll give you this equation on the exam. But since you have presence of this weak acid, presence of this conjugate base, what will you use? Okay, the Henderson-Hasselbalch equation. Okay, and this equation is this. pH is equal to pKa. pKa is minus 4.5 times 10 to the minus 4 plus log, drop the acid. Okay, drop the acid, which is HNO2, 0.0112 and 0.0444. So on my calculator, this is 3.35 or so. 0.0444 divided by 0.0112. Let's log that. .598. Okay, when I add this and this together, just check your calculator with mine for the test. Okay, I'm getting 3.95. Okay. So this is what you do before the equivalence point. Part A is what you do when nothing is added from the burette in the titration. And now we're going to go through something even more crazier at the equivalence point. Okay, are you guys ready for this? All right, what is the pH at the equivalence point? First of all, what is the equivalence point? Okay, it is when the titrant, in this case it's OH minus, is equal to the titrand, the thing that's sitting in the flask, and that is HNO2. All right, so do you guys remember this from Chem 1? M1V1 equals M2V2. Okay, we want their concentrations to be the same. Okay, we have OH minus in the burette. We have the weak acid sitting in the flask. This is called the titrand. The OH minus that we drop is the titrant. So the molarity of OH minus, let's go all the way back here, is 0.10. How much are we going to add of that OH minus? It's not 80. We added 80 in part B. What's the concentration of the weak acid? We have 100 ml and 0.10 molar. 0.10 molar, 100 ml. All right, so solving for V1, I am getting 100 mLs. 0.1 times 100 is equal to 0.1 times 100. So it takes 100 mLs of 0.10 molar OH minus. Okay, to completely react with the 100 ml of 0.10 molar HNO2, weak acid, nitrous acid. All right, that's when they're equal. Right, now, what is the concentration after mixing? I need everyone's attention to be with me here. Okay, concentration after mixing. Okay, let's first do the OH minus. Okay, let's first do the OH minus. Okay, so how much will neutralize the HNO2? Okay, we calculated using this equation 100 mLs. The concentration of the HNO2 in this problem is, what's the concentration? 0.10 molar. What's our total volume? What's our total volume here? $200. Very good. So this is 0.050 molar. Okay. Now let me ask you this question. I need you guys to be with me, focused on the paper and me. Equivalence point. What's the concentration of HNO2? equivalence point. What do you think it's going to be?
Would be 0.0500.
Very good. Okay, 0.05. Why is it 0.05?
Because they have to be equal to each other.
At the equivalence point, they have to be equal to each other. Okay, very good. Nice job. All right, so here we are at the equivalence point. So what's the equation here? Okay, so we have HNO2. We put in, this is part C now, at the equivalence point, plus OH minus. It's a strong base, so it's going to take all of it, all of this weak acid, and it will give us H2O liquid plus NO2 minus. Okay. All right. As Bailey mentioned, we figured out the concentration after mixing. It's 0.05, and because it's the equivalence point, the other one is also 0.05. Okay, don't worry about this liquid water. All right, Bailey, I'll ask you this. I think you're my partner in crime here, or partner in lecture. How much of this strong base will eat up this weak acid HNO2?
It'll eat up all of it.
Okay, how much is all of it?
0.005.
0.05, yes. It is 0.05, right? Yeah, 0.05. All right, do you guys see a problem here? Do you guys see a problem? What's our problem? I see something totally messed up here. How is this possible? Zeros? Now what will we do? How will we get the pH? By the way, we have to calculate the pH. How will we get the pH at the equivalence point? What do you guys think? This is part C. I'll pick on you, Carolina. Pick on you. So, what do you think we'll do? First of all, look at the arrow here. Okay, the arrow tells us this is at an equilibrium. So if this is going this way, what else can it also do? Okay, you got it. She got it. Okay, she got the right answer. So for at the equivalence point, what do you need to do? You have to use the back reaction. Okay, good job. Okay, you have to use the back reaction. So we will use the back reaction. Okay, so the back reaction is this. It's NO2 minus. Goes to HNO2 plus OH minus. Okay, so this NO2 is going to be 0.050. Okay, 0.0500 M. Okay, don't care about the water. This is 0, 0. All right, I'll ask you this, Carolina, right? Not Carolina, Carolina. North Carolina, South Carolina, and Carolina. Okay, I'll give you 1,000 bonus points if you're able to answer this question. What reaction is this? Now think about this. We have this weak base reacting with water, giving you OH minus and its conjugate acid. What is that K called? It's not KW. Remember, it's giving us OH minus. So what will it be? K, I think you said it. Very good. This is KB. How will we find KB, though? How will we find KB if in the problem they gave us KA?
We divide KW by KA.
Excellent. Okay, you guys have to remember KA times KB is equal to KW. Okay, both of you did a marvelous job, so thank you. All right. So we will get KB because this reaction describes KB, as Carolina said. This reaction describes KB. So we will take the KW and divide it by KA. KW, I'll give you that, but to be honest, I really would like for you to memorize it as 1.00 times 10 to the minus 14. The KA is 4.5 times 10 to the minus 4. So what is that on our calculator? I'm going to do this super quickly here. Getting 2.222 times 10 to the minus 10. Okay, so this is the equation for KB. We calculated KB from KW and KA. I think we're good now. Minus x plus x plus x. 0.0500 minus x plus x plus x. Okay, we'll plug that into KB now. Not KA, because as our classmate said, KB is what's happening here in the back reaction. So it's going to be KB is going to equal to OH minus times HNO2 divided by NO2 minus. Okay, we just calculated KB as 2.22 times 10 to the minus 10. HNO2 is x, OH minus is x times x is x squared divided by 0.500 minus x, or 0.05 minus x. All right, we will assume x is small. Okay, this is called the low ionization assumption. So 0.0500 minus x is about 0.0500. This is the low ionization assumption. You guys can check my math along the way. Times 0.05. So doing this on my calculator, I'm getting 3 times 10 to the 6. 3.33 times 10 to the 6 minus 6. But what does that x really symbolize? What does that x really mean? Of what? Of OH. So before calculating pH, what do we need to calculate first? Are we going to calculate pH or what?
You have to find pOH.
Correct. Say it with more confidence. That's correct. pOH. All right, so we will calculate pOH, which is minus the log of OH minus, which is minus the log of 3.33 times 10 to the minus 6. And I'm going to do that really quickly on my calculator just to save some time here. We get 5.48. Hopefully that's the right answer. So I'm getting a pH of 5.48, provided I did all my calculations correctly. Okay, 2.17, 3.95, 5.48. All right, this is what happens when it's at the equivalence point. What will you do? What will you use at the equivalence point? Okay, you're going to use the back reaction.
So That's
Oh, wait a minute. That's not the right answer. What is the right answer? Damn it. Yes. Oh, I'm so stupid. Okay, so the pH is going to be 14 minus 5.48. Thank you.
Also, no, wait, that don't sound right.
8.52. Okay, so sorry about that. Okay, 8.52. Okay. Okay, this is the POH. The pH is going to be 14 minus that, which is 8.52. Okay, so please don't do what I did. This is the POH. Okay, from the POH we will get the pH. All right. Right, so can we do this? Okay, we first figure out the concentrations. That will give us the equivalence point. We use the back reaction, and the back reaction is Kb. From Kb, POH. POH will get the pH. All right, the last one here is after the equivalence point, and that's part D. So let's go now to page 8. This is after the equivalence point. (105 mLs of NaOH are added. So first thing you'll do is concentration after mixing. Okay, so what would OH minus be, concentration after mixing? Okay, we took 105 mLs of NaOH. What is the concentration given to us in the problem? It's 0.10 molar. Okay, what's our total volume? Okay, it's 105 added to 100 mils of HNO2, right? 800 mils. So what's our total volume after we add 105? 205? Mils cancel. So what is this on our calculator? I'm going to do this really quickly now. Divided by 205. I'm getting 0.0512 molar. Okay, we'll do the same thing now for the HNO2. And this is 100 mLs times 0.10 molar divided by 205 mLs. Okay, because we have 100 mLs of HNO2. The mils cancel, so what is that? I'm going to do that super quickly here. 0.0487. Okay, so we add from the burette 105 mLs of sodium hydroxide to the NaOH, to the HNO2, I'm sorry. Our OH concentration is 0.0512. Our HNO2 concentration after mixing, this is part D now, is 0.0487. Okay, don't worry about the water, it's a liquid. Okay, the NO2 minus is 0. All right, Bailey, I'll ask you this. How much of this OH minus will eat up this weak acid HNO2? All of it. So how much is all of it in this case? How much is all of it?
0.0487.
Very good. Okay, 0.0487 molar. All right, so this is 0. This is 0.0487 molar. Okay, 0.0512 minus 0.0487. getting 0.00242. Okay, something like around this. 0.051. Oh, let me just do it here. Yeah, okay, 0.0025 or 0.00242. All right, so how will I, yeah, go ahead.
So in part B, we subtracted the OH from the HO2.
Yeah, because it took all of it, but all of it is 0.0444. Okay, you can't take 0.0556 because you only have 0.0444.
Oh,
And on the flip side, Carolina, in part D, eat all of it, and all of it is 0.0487, leaving us behind about 0.00242 OH minus left over. So with this OH minus left over, 0.00242 OH minus left over, what can we do? We'll calculate the POH, right? POH, which is minus the log of the OH minus and minus the log of 0.00242. Okay, and what is the POH here? I'm getting about 2.62. I'm not going to make this mistake like I did in part C. Okay, what is the answer? What is the pH? It's going to be 14 minus this. And what's 14 minus 2.62? About 11.38. Okay, so the answer here is 11.38. All right, so nothing added before the equivalence point, at the equivalence point, and then after the equivalence point. Okay. All right, so at the equivalence point, what are we going to use? We're going to use the back reaction. Okay, we will use the back reaction. So here's an example of at the equivalence point. I will let you guys do this, and then I will post the answer up. Okay, so do this as a practice problem. Okay, what will you use here? The back reaction. What is the what is the equivalence point? It is when your titrant is equal to your titrand. Okay, so that's what happens at the equivalence point. And then what's the reaction here? It's going to be CH3NH2 plus H plus. I'll use H plus as H3O plus, okay, because it's a strong acid. Okay, this is a weak base. This is a strong acid. You'll get CH3 NH3 plus H2O. Okay, this is the reaction that you will get when you react methylamine with HCl solution. Okay, so with that, we'll calculate the concentration after mixing, and like Carolina said, we'll use the back reaction. Okay, so I'll let you do that. I'll post the answer up. And then let's just move on to KSP here. All right, so calculating the pH at the equivalence point. What will you use? Which type of reaction? The forward or the back? You will use the back. Okay. At what part of the titration? Before, after, or at the equivalence point? You will use the back reaction at the equivalence point. All right, I'll post the answer up. You can check your work with mine. Make sure you do this as some extra practice. How are we on time? That computer blacked out on me. Okay, looks like we have about 8 more minutes. Okay. All right, so do you guys know about KSP here? Okay, so KSP is our next type of equilibrium. Okay, and we will use this for sparingly soluble solids. Okay, sparingly soluble solids. So in this case, okay, we have an equilibrium, but what is in the reactant side of the equilibrium? A solid. So some of the solid goes back. Okay, do you remember that lab last week you did where you had to take that precipitate and split it into 3? One in case it mess up, the other one you put in 40 mils water, the other one you put in 80 mils water. Okay, you're taking that calcium iodate, which is the sparingly soluble solid, and then some of it will go back to its ions. Okay, so let's take a look at calcium phosphate. Let's look at this example. So this solid is in an equilibrium with calcium ion and phosphate ion. Yes, ma'am. Okay. Okay. So this would be the KSP for calcium phosphate. Okay, and the KSP, I'll give you the KSP. Okay, it's 1.2 times 10 to the minus 26. Okay. Right, we balance this. Okay, so to balance this, I'll put a 2 here and a 3 here. All right, so for KSP for the ice table, first of all, okay, don't worry about the solids and don't worry about the liquids. But some of that solid will go back here. And it's going to be plus, we don't use X, we use S. And this one will not be plain old S. It will not be just S alone. But how much S? Because of the balanced equation, it will be 3S. Okay, some of it will go back here. This will not be S, but how much S? Okay, so the S stands for solubility. How much of it goes back in water? Okay, so we don't use X like you did in all these other ice table problems, but you use S. Here the S stands for solubility. Okay, so the KSP is equal to the concentration of calcium ions. We'll cube it because there's 3 times the concentration of the phosphate. We'll square it because it's 2. Alright, so this is going to be 3s cubed times 2s squared equals KSP. I'll give you that KSP. 1.2 times 10 to the minus 26. Alright, 3s cubed is 27s cubed. 2s squared is 4s squared. 27 times 4 is 108. And then s cubed times s squared is s to the power of 5. Okay, so we're figuring out the solubility. How much of this goes back this way? All right, so s here is going to be 1.2 times 10 to the minus 26 divided by 108. Okay, we don't square root it, but we fifth root it. Fifth. Okay, to the power of 1/5. So this is how you do these types of problems. If it's asking you to find the solubility, how much of this goes back this way for the KSP sparingly soluble solid. Okay, so this is the fifth root. If you take the square root, it's to the 1/2. Cube root to the power of 1/3. Fourth root to the power of 1/4. Fifth root, like right here, to the power of 1/5. Okay. So 1.2 times 10 divided by 108. Okay, we're going to take that to the power of 1/5. And we're getting about the S to equal to 2.5. Okay, we'll do 2.6 times 10 to the minus 6 molar. So let's say you have, this is moles over a liter. This is moles over a liter. So let's say you have calcium phosphate, and some of it's going to go back there. Okay, some of it will go back dissolved in water. So if you have 1 liter, the calcium out of calcium phosphate that goes back dissolved in water as calcium ion will be 3 times this S. Okay, so this is how you do your KSP problems, which is about 7.7 times 10 to the minus 6 molar. And let's say you have some calcium phosphate solid. You have 1 liter solution, but you have this solid. Some of it in 1 liter will go back this way, dissolve in water as phosphate ion. That's going to be 2 times S. And that is 5.2 times 10 to the minus 6 molar. So this is a little bit more complicated because you have a 3 and a 2. Okay, but something like AgCl, if you look at AgCl, which is just 1 to 1, it's just equal to S. It's just equal to S. I think I am out of time here. Yeah. So we will continue to do this next Tuesday, and then we'll see where we are on the exam, whether I need to postpone it again. I have last week's lab report, so if you're here, I could give that to you. All right, make sure you work on your Chapter 16 homework. Try to get ahead. Make sure you work on this lab problem set with your group.